When stars die, what happens next depends on how massive they are. Smaller stars, like our Sun, slowly shed their outer layers and leave behind a dense core called a white dwarf that slowly cools over time. But giant stars go out in a far more dramatic way, exploding in a supernova, one of the most powerful events in the universe. After that explosion, the core may collapse into a neutron star, or, if it's massive enough, form a black hole. In death, stars actually help create new elements that go on to form planets, and even life. Today we will talk about what happens when stars die. So before we start, make sure to hit the like button and subscribe to my channel. 1. The formation of stars inside nebulae and the start of stellar life. Stars are born inside massive clouds of gas and dust called nebulae, which are spread across galaxies and serve as stellar nurseries. These nebulae are composed mostly of hydrogen, along with helium and trace heavier elements produced by earlier generations of stars. Over time, slight disturbances, such as shock waves from nearby supernovae or gravitational interactions, cause regions within the nebula to collapse under their own gravity. As the gas collapses, it fragments into denser clumps that heat up and form protostars. During this phase, the object is not yet a true star because nuclear fusion has not begun. As gravitational pressure continues to increase, the core temperature rises dramatically until it reaches around 10 million Kelvin. At this point, hydrogen nuclei begin to fuse into helium, releasing enormous amounts of energy. This moment marks the birth of a star and the beginning of a long journey governed by a balance between gravity pulling inward and energy pushing outward. 2. Hydrostatic equilibrium and the long main sequence phase. Once nuclear fusion stabilizes, the star enters the main sequence phase, which is the longest and most stable period of its life. During this stage, the star maintains hydrostatic equilibrium, a delicate balance between inward gravitational force and outward pressure from fusion energy. In the core, the star essentially burns hydrogen into helium, although it is actually nuclear fusion rather than combustion. The duration of this phase depends heavily on the star's mass. Low-mass stars, such as red dwarfs, consume their fuel very slowly and can remain stable for trillions of years, far longer than the current age of the universe. Medium stars like the Sun remain on the main sequence for about 10 billion years. High-mass stars, however, burn through their hydrogen rapidly due to extreme pressure and temperature in their cores, causing them to live only a few million years. The Hertzsprung-Russell diagram helps astronomers classify stars during this phase by plotting their brightness against surface temperature, revealing clear patterns in stellar evolution. 3. Exhaustion of hydrogen and the transformation into giant stars. When hydrogen in the core is exhausted, the star's internal balance begins to collapse. Without sufficient fusion pressure in the core, gravity causes it to contract, increasing temperature and pressure in surrounding layers. This triggers hydrogen fusion in a shell around the core, while the outer layers expand significantly. For Sun-like stars, this leads to the red giant phase, where the star can grow hundreds of times larger than its original size and become much more luminous despite a cooler surface temperature. For massive stars, the result is a red supergiant, which can become so large that its outer envelope extends beyond the orbit of Mars or even Jupiter if placed in our solar system. During this phase, helium begins to fuse into carbon and oxygen in the core, marking the start of more advanced nuclear reactions. The star becomes unstable, often pulsating and losing mass through strong stellar winds. 4. Advanced stellar nucleosynthesis and the onion layer structure. In massive stars, fusion continues beyond helium in a process called stellar nucleosynthesis, where increasingly heavier elements are created. In successive stages, the core develops an onion-like structure, with each layer undergoing different types of fusion. Helium fuses into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. Each stage occurs at progressively higher temperatures and lasts for shorter periods, with the final silicon burning stage lasting only days. Iron represents a critical endpoint because it cannot release energy through fusion. Instead, iron fusion requires energy input, making it impossible for the star to sustain itself once an iron core forms. As iron accumulates, the core becomes increasingly unstable, eventually reaching a threshold where electron degeneracy pressure can no longer support it. This sets the stage for catastrophic collapse, marking the final moments before stellar death. 5. Core collapse and the cataclysmic supernova explosion. When the iron core exceeds the Chandrasekhar limit of about 1.4 solar masses, it can no longer resist gravitational collapse. In less than a second, the core collapses inward at a significant fraction of the speed of light. Protons and electrons are crushed together to form neutrons, releasing an enormous burst of neutrinos that carry away most of the gravitational energy. The inner core stiffens suddenly, causing the collapsing outer layers to rebound violently. This rebound generates a powerful shock wave that travels outward, ripping through the star and producing a supernova explosion. A Type II supernova, which results from the collapse of a massive star, can briefly outshine an entire galaxy. The explosion ejects vast amounts of gas and heavy elements into space at speeds exceeding 10,000 kilometers per second. These elements, including carbon, oxygen, gold, and uranium, are essential for forming new stars, planets, and eventually life. Supernovae are, therefore, not only destructive but also creative events in the cosmic cycle. 6. Neutron stars, the ultradense remnants of stellar cores. If the remaining core after a supernova has a mass between roughly 1.4 and 3 times that of the Sun, it collapses into a neutron star. Neutron stars are extraordinarily dense objects, packing more mass than the Sun into a sphere only about 10 to 20 kilometers in radius. The density is so extreme that atomic structures collapse and protons and electrons merge to form neutrons. A sugar cube-sized amount of neutron star material would weigh billions of tons on Earth. Many neutron stars rotate extremely rapidly due to conservation of angular momentum, sometimes spinning hundreds of times per second. These fast-spinning neutron stars are called pulsars because they emit beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep across space like lighthouse beams, producing highly regular pulses detectable from Earth. Some neutron stars also become magnetars, possessing magnetic fields trillions of times stronger than Earth's, capable of disturbing atomic structures at great distances. 7. Black holes, the final collapse beyond known physics. If the collapsed core exceeds approximately 3 solar masses, gravity overwhelms all known forms of pressure, including neutron degeneracy. Pressure, leading to the formation of a black hole. A black hole is an object where space-time is curved so intensely that nothing, not even light, can escape once it crosses the event horizon. The event horizon is not a physical surface, but a boundary marking the point of no return. At the center lies the singularity, a region where density becomes infinite and the laws of physics, as currently understood, break down. Black holes can range from stellar mass black holes formed by dying stars to supermassive black holes found at the centers of galaxies. Although black holes themselves are invisible, their presence can be detected through gravitational effects on nearby stars and through X-rays emitted by hot gas and accretion disks. But if you like this video and would like to see more like it, please give it the thumbs up, leave a comment, and click the button to subscribe.